of the 2021 Meteorology and Market Design for Grid Services Workshop. I'm Mark Ahlstrom, President of the ESIG Board of Directors and VP of Renewable Energy Policy for NextEra Energy Resources. For those of you not familiar with ESIG, we are a global member-based nonprofit organization providing objective information, resources, networking, and opportunities in support of renewable energy and energy systems integration decisions. We do this through workshops, tutorials, webinars, blogs, working groups, and task force activities, and by producing technical resource materials and briefing materials for decision makers. Our virtual workshops and monthly webinars are free and open to everyone, so please learn more and register. You can find us on the web at esig.energy. Send an email to info@esig.energy to get our monthly newsletter and follow up our activities at LinkedIn, Facebook, and Twitter. ESIG is also serving as a leadership role in the Global Power Systems Transformation Consortium, often called GPST, whose mission is to bring together key actors from around the world to catalyze a rapid clean energy transition at unprecedented scope and scale. ESIG leads the first of 5 pillars that deals with the agenda for the system operators. For more information on GPST, you can check www.globalpst.org. All ESIG workshops have been online events during the pandemic, which is a big change from our wonderful face-to-face workshops. And a number of you have asked me how ESIG has been doing. The answer is very, very well. Our member organizations stuck with us, new members have joined, and growth in foundation funding for the ESIG mission has been very strong. In fact, we've roughly doubled our foundation funding, our overall funding for ESIG as well, and that has allowed us to double our staffing, our task forces, and our participation in many events over the last year. For full-time ESIG staff, in addition to Executive Director Charlie Smith, we have now added Debbie Liu as Associate Director and Ryan Willis as Director of Marketing and Operations. In addition, Professor Mark O'Malley is on full-time assignment to ESIG to lead ESIG's key role as a core member of the Global Power System Transformation Consortium. ESIG is now running major task force projects on rethinking resource adequacy, macrogrid transmission, grid forming inverters, open system participation of distributed resources, system flexibility, and hybrid resources. We are increasing our training, materials, and briefing documents for decision makers that come from what we collaboratively create together at ESIG. And we do plan to start, again, face-to-face events, with our first major in-person event being the Fall Technical Workshop in Austin, Texas, during the week of October 25th. Please mark your calendars, and we'll be sending details soon. Also, be sure you are receiving our monthly newsletters, and if you're not, send an email to Ryan at info@esig.energy to request a newsletter or with any questions, and we'll keep you informed of all the activities and events. Today, however, is the first session of the 2021 Meteorology and Market Design for Grid Services Workshop, and we'll be holding this entire workshop this month as a series of panels using WebEx. The next session after this one is the opening plenary panel on meteorology and climatology this Friday. It'll be discussing major weather-driven February events in Texas and Midwest that many of you have heard about. We then continue on Tuesdays and Thursdays during the rest of June. The workshop will wrap up on June 29th with a closing plenary panel discussing how the combination of such weather events and grid transformation more broadly may call for changes in our view of resource adequacy and market design. I hope you're able to join us for all these sessions of wonderful speakers. Each session is provided at no charge, and you can register in the events area at esig.energy to get the WebEx link that is individual for each session. The primary source of support for making all this possible is annual memberships, and I thank you if your organization is a member and strongly encourage you to consider joining if you are not currently a member. The modest annual membership fee is based on the annual budget of your organization. And if your organization has a membership, then everyone in your organization is a member of ESIG. Independent consultants and individuals can also join, and ESIG provides free memberships to students of accredited educational organizations. ESIG is a great place to learn and share your expertise, and we all need to do whatever we can to bring talented people into our industry and get them working on the important issues. In addition to the major support from the memberships, I'm very thankful for the long time and ongoing support of the U.S. Department of Energy, the sustaining membership of NextEra Energy, and I particularly want to thank Analytics, powered by Polaris Systems Optimization, for again being the workshop sponsor for this workshop. The support of these organizations reflects the significance of ESIG for power system transformation efforts more broadly. Just a few logistics. First of all the attendees will be muted for the webinar to avoid distractions. For the Q&A, we are using the Slido platform. So to ask questions, go to slido.com in a web browser and enter ESIG1, ESIG1 as the event code. The instructions are also provided at the bottom of the screen that you're seeing here. You will see a thumbs up button next to the questions to allow you to cast votes that have already been submitted to help prioritize the questions that we will ask first. We plan to save about 15 minutes for Q&A at the end and then wrap it up at the top of the hour. And yes, the session is being recorded, and we'll email you the slides and link to the recording. And also, if we can't get to all the questions, we will plan to distribute short responses to unanswered questions after the webinar too. So don't be afraid to submit any questions through Slido. Now to kick off our workshop, it's my great honor to introduce Gary Gearnard, Director of the Earth and Environmental System Sciences Division of the U.S. Department of Energy. Gary previously served as Director of the Institute of Geophysics and Planetary Physics for Los Alamos National Lab. He was also formerly Director of Atmospheric Environment Department for the Environmental Research Institute in Denmark, and Program Meteorology for Marine Meteorology at the Office of Naval Research. He has a PhD in atmospheric science from University of Washington, as well as a postdoc from the Naval Postgraduate School. I'm sure that his thoughts on weather and climate as components of energy planning, risk analysis, and decision-making will lead to interesting questions and discussion following the presentation. So Gary, the podium is yours.
Thank you, Mark, and thank you everybody for joining this opening of this workshop. I have to say the title I gave for my talk today is not very creative. It's really the name of the workshop itself. But given that my background is in meteorology, I'm going to put more weight on that side, but at least cover the gamut at a very high level of how meteorology, the energy sector, grid services, how they're interdependent and how we really do need each other to go forward. So before I jump in, I wanted to at least provide a few definitions because there has been some confusion of what is weather versus what is climate. So I thought I'd at least lay this out to at least set the stage. But when I talk about weather, I'm talking about the instantaneous conditions in the atmosphere. You know, these are hourly, daily, weekly, all the variabilities, the magnitudes of, say, temperature, precipitation, wind speed, that kind of stuff. And when we look at forecasting the weather, we use what they call deterministic models. In other words, you initialize the models based upon a field of data out there, and let's say over the planet. And once the models are initialized, they progress forward in time and make forecasts as you move out, let's say hours, days, and up to around 10 days is about as good as they can go. The confidence really degrades quite quickly as you march towards 10 days. And that's really the let's say the shortcoming, but it's just a fact of how you do deterministic models. On the other hand, we have climate. And climate is really what I call the long-term average of weather that extends over multiple years or even multiple decades. So we characterize climate change or climate models, at least stochastically. So we're looking at things like low frequency trends, looking at variabilities caused by things like El Nino. Also extreme events, which are embedded within the system, but it's a totally different approach. It's not using deterministic, but it's stochastic. In other words, it doesn't degrade so much over time, but the role of energy policy does play a significant role as you get beyond, let's say, 2 or 3 decades in the future. In the middle, that S2S, subseasonal to seasonal, is in that no man's land that falls between weather and climate. It's a tough challenge for the meteorological community because it blends the whole area of deterministic forecasting with stochastic forecasting. It's one of the biggest challenges facing the US community, or let's say the international community. And that's also a key component of how we do energy projections, at least nationally or even globally. Going on to my next slide, I just wanted to lay out 4 areas I wanted to focus on. I'm not going to read these, but at least you can see right now the kinds of topics I'm going to skim through as we go forward with this presentation. And keep in mind, these are all at a high level because I recognize that subsequent meetings of this workshop are going to get into the details of how meteorology, energy, and let's say grid services start to interact. So a few national challenges. I thought I'd lay this out because especially with this administration coming in and making a lot of, developing a lot of agendas in energy security, they are tying it quite closely to what I call climate solutions. And I put 4 bullets up here to illustrate that. And the intent is to design and deploy low carbon emitting technologies and get them out into the sector as quickly as one can. But it really depends upon demonstrations, which really rely upon the research and the operations communities really working together. The second one is not new. This has been, let's say, a priority for, I would say, the last many decades. And that is the government and the public really are demanding uninterrupted and affordable supply of energy. And that is not an easy ask for all of us, because every time there's an extreme event, we do face the risk of interrupted supply. And the challenge is, how do we design the system to at least overcome that and make sure we can at least satisfy that particular challenge? The third one I put up here is what I call the dynamic distributed grids, so which incorporate energy storage. And when I talk about dynamic, it's not just the classical grid that we have for different sections of the US, but it might be how do we incorporate microgrids, other types of emerging technologies involving the grid and energy storage, and making sure that we can at least package that together in a way that makes sense and at least can provide some, let's say, support to the kinds of challenges we're trying to satisfy. The second big bullet is on international competitiveness, because that's a major factor, not just in this administration or the previous one, but I think it's going to be the same going forward in time. And that is that as we start to develop, especially wind, photovoltaic, or broadly this whole solar energy enterprise and beyond, who is going to capture those markets in the international? It could be the US if we play our game right, it could be other countries, but this is a key component of how energy and economics, meteorology, how all of these agendas start to package together. And the final one on public expectations, I think you can see that, but especially the third bullet on equitable solutions has become a major issue, at least during the past months. And that's also very present if you read the president's budget request that was released on Friday. Okay, I wanted to segue from that slide to at least get one layer below, and that is looking at the various sectors within energy and meteorology, and at least identify at least what we view to be some key challenges that we need to pay attention to. And the first I have in this bullet is in decision making. And I've given a number of talks in the past where I focused on the need for uncertainty quantification in every type of projection or prediction. And the reason I put so much weight on that is that if one looks at decision making from the view of the finance sector or the risk sector, what they often do is look at all of the various components going into a decision tree. And for each of those components, they're going to examine what the level of uncertainty is for the predictions or the projections. And if the uncertainty is above some threshold, it's unlikely that they'll use the information. So a challenge for the scientists is, how do we get that uncertainty down to some acceptable level, let's say below a threshold, where decision makers will actually use the information? And that, of course, changes depending upon which question is asked. But the main thing is, we have to get the uncertainty down, we need to quantify it, and we need to put the uncertainty within the model predictions in the context of the uncertainties within the decision codes that are being applied for risk and finance or any other type of application. The second big bullet is that the IPCC and the National Climate Assessments have been providing a lot of information to stakeholders across multiple sectors, including energy. But there are some shortcomings with a lot of these models that go into these big assessments. The biggest one is that they're often at 50-kilometer or 100-kilometer resolution at best. And what that often does is that it limits the quality and the accuracy of a lot of the projections, especially in regions that are becoming very popular within the energy sector. And when I say popular, it's often looking at, say, offshore wind or mountainous terrains, areas where 50 kilometers or 100 kilometers just isn't good enough. There might be some horizontal gradients, a lot of extreme events which are more local, that it might be tied to coastal regions or the mountainous terrain. But these are big issues that we need to deal with in the scientific community, because we have to make sure that we can satisfy the needs of the energy sector in a smart way. And that's going to rely upon getting much finer resolution projections that at least get down to the scales where a lot of these extreme phenomena that we know exist and are affecting the operations of many components of the energy sector. And the last big bullet on the bottom is that we need a systems approach to look at vulnerability and risk. And it's not just the systems across the energy sector, but other sectors like water. The energy water nexus becomes important, especially because if we look to the West as a good example in drought-prone years like we're in today, the energy water nexus becomes important because hydropower, for example, becomes a really critical component. And I'll show a slide in a few minutes which illustrates that point. But the other thing about the energy water nexus and looking at longer timescales is that when we examine the financing of energy in the future, we're looking at two dominant timescales: the bond financing timescale, which is often about 30 years, but also the infrastructure, especially base infrastructure, is also expected to last 50 to 100 years. So we have these two timescales to deal with within our decision making, and that's a challenge because, again, it relies upon a good handshake and working relationship between the meteorological sciences, the energy engineering professions, and the operations community all working together. Okay, so I think I might have skipped over a slide. Let me pull that back. Okay, here's a view that I have here. I wanted to mention about the engineering sector, and that is that the wind power sector has been making some radical changes over the last, at least, well, under the design phase for the past decade, but more recently over the past 3 to 5 years. And that is what I call the challenge of the really large turbine. Now, what I mean by a large turbine, I'm talking about turbines from the surface extending up to, say, 600 feet. I mean, these are quite high in the boundary layer. And very often these turbines are being designed to be deployed within coastal regions or other regions that do involve a lot of really strange atmospheric phenomena sometimes. And it becomes a challenge, not just for the meteorologists, but also for the energy sector to have to figure out how do we weigh the balances and how do we improve the science so that we have a better grasp of what kind of conditions are likely to be experienced under such a large vertical extent of wind power production. So that's a key point I want to pull out. I'm going to revisit that point in just a minute. Solar energy facilities on the grid, the same type of problem, but it's a little bit different in the sense that these don't rely upon heights within the boundary layer. They're more about aerial coverage. But the models which are currently used often are at very coarse resolution. So if we're looking at changes of solar potential based upon cloudiness in the future or any other type of, let's say, solar input, we need models and we need observational systems that better get a grasp on what the possibilities might be. And finally, grid dynamics. I think this is a pretty standard knowledge across the community on this call. But looking at grid dynamics, load balance, and stability, it's not just the classic grid that we've had over the past decades. but incorporating microgrids, energy storage, other types of phenomena that we hadn't had to deal with decades in the past, but it's becoming more and more common with the plans that we see underway across the community. Okay, so next slide is into the whole meteorological community, and that is, what do the weather models tell us right now that maybe need to be improved, and what are their shortcomings? And now we're getting more into my personal areas of expertise, but the main thing is local area models can really get to 1 kilometer resolution, and that really is ideal for the kinds of meteorological phenomena that we're going to be experiencing, especially in coastal regions or other mountainous heterogeneous regions. But in terms of forecasting, it's typically much coarser grid. It gets to about 10 kilometer resolution. And I think the game going forward is how do we nest local area models within a weather forecasting system, and even incorporate stuff like large eddy simulation to get some better understanding of how much turbulence variability might there even be within 1 kilometer. But I think you can see that this is the direction that the research environment is moving towards, and that is, let's say, scales of different types of models that can work closely together, nested within each other. And I think that's going to be a challenge to not just develop the science, but how do we demonstrate that with the engineering communities in a way that makes sense for them. So moving to the ideal case, I mean, I grew up in the boundary layer meteorology community and I lived that for several decades. The ideal world and the simplest world is looking at flat terrain, homogeneous conditions, relatively stationary conditions, a deep boundary layer. All of those kind of line up, and especially what I would call neutrally stratified conditions. These are all very idealistic. We don't often experience those in some of the regions where at least wind power is being deployed. And I would say that's becoming not just an opportunity and a challenge for the atmospheric sciences, but it's also a way for the communities to start working together. So where do the predictions really break down in terms of weather forecasting? And that really is in the heterogeneous complex terrain, coastal regions, mountains, other types of regions which seem to be popular for the deployment of, say, wind power systems. But in some of those regions, you do experience low-level jets. We get internal boundary layers that form. We get gravity waves at the top of the planetary boundary layer, non-stationary turbulence. These are some among the tougher problems in the atmospheric sciences. And I would say the science is being driven in large part by the needs being generated by the wind power and the solar power and other types of energy communities. So in a way, I'm thanking you guys for providing these opportunities, but it's also creating, let's say, a kind of nightmare for us, but it's an exciting nightmare because it tests our, let's say, it tests the possibilities of where do we need to go, how do we advance our models with more powerful computers, and how do we design the observing systems which can be married to the modeling architectures for demonstration. Anyway, the climate models need to also incorporate the same type of features being developed by the weather models. But they operate at coarser grids. These climate models are not typically used for operations, but instead they're being used for, let's say, designing future systems so we can get a better handle of what kind of extreme events they might encounter over their lifetimes, planning and looking at financial risk issues. So just to illustrate the kinds of conditions we might encounter, this is an illustration of offshore deployed wind farms of really deep wind turbines. And these are the kind of conditions where I can actually look in the distance in the slide. You can see the coastline. And if there were offshore flow during stably stratified conditions, it wouldn't be unusual for an internal boundary layer to be within the aerial coverage of that wind turbine. And what that often can do is generate very severe wind shear across that entire system. So getting a handle on what types of wind shear can be predicted with finer resolution models, that's the challenge for the meteorologist to figure out. But at the same time, It's a reality. We're moving into these types of geographic domain. And it's also a reality that we need to work together to at least solve this problem collectively. So the coarse grid models for climate are a different animal. They don't look at so much the types of internal boundary layers, the weather models might think about, or the turbulence variability caused by, let's say, a gravity wave breaking at the top of the boundary layer. But it's looking more at the lower frequency phenomena, like, are there going to be El Nino oscillations that might change in the future? Or would there be an Atlantic oscillation that might change into the future? So these are the kinds of issues which we do pay attention to in the climate community. And I would say the biggest challenge for us, I'm saying us because I manage those portfolios within Department of Energy, and that is, how do the PDFs of weather variability and extremes, how are they going to change into the future? We all know that we're going to be experiencing warmer extremes. We're going to be experiencing probably more severe storms in some regions, but maybe not all regions. But how do we get a better handle on how those PDFs are going to be changing over, let's say, half decade increments going into the future, or decadal increments? And more importantly, are these modes of variability, such as El Nino and the Pacific Decadal Oscillation and Atlantic Oscillation, are they going to start interacting in different ways into the future? So this is a big challenge for us. And I wanted to point out by looking at that figure in the lower right-hand side, and that is that at least for the next 20 years, it doesn't matter which energy policy we invoke. We're going to get the same type of warming, the same type of climate change. It's really beyond 2040 or 2050 where we start to notice how a different emission reduction policy might play out. But again, the base infrastructure for the designs are going to be extending up through 2100. So these energy policies are becoming important in figuring out how we do stuff. So the climate patterns and modes of variability, this gets into a bit more detail of what I mentioned in the last slide. I wanted to point out that it's not just the North Atlantic Oscillation, but there are lots of them. I've listed on the upper left-hand side of this chart. People often think about El Nino here in the US, because the El Nino does exert some signature over precipitation patterns, heat patterns in the American West especially. But if you're in Europe, you don't think about El Nino as much as we do. They might think about the North Atlantic Oscillation, the NAO, because the NAO is something which does influence the wind patterns that might occur seasonally or even annually or different parts of Europe. They put a lot of effort to understand that. But for other parts of the planet, you might have different oscillations they pay attention to. But from a climate perspective, we need to figure out how they all develop over time and how they all interact. And these are going to become important for figuring out what kind of exposure could we experience in different parts of the planet as we start to design and deploy different types of energy systems in different regions. I'm going to put this slide up especially because there's been a lot of attention recently to extreme events. These can actually bring down infrastructures. We have cascading failures when many of these occur. And this is, I would say, all of these photos were taken during the past 2 to 4 years. The one in the lower right is probably the most recent one from Texas earlier this year. But in every case, we're seeing severe events that with increasing frequency and magnitude that we had not experienced so much decades into the past. So getting a handle on how these are going to be playing out into the future relies upon much finer resolution climate models than we've been playing around with for years. The IPCC class models are typically 50 to 100 kilometer resolution. They're moving towards 25 kilometer resolution. But I'm going to illustrate something which DOE is investing in. We're actually moving towards 3 kilometer resolution, and I'll show you that in just a moment. But the main point is, without getting a better handle on how extreme events are going to be playing out into the future, we're not going to make sufficient progress in analyzing how to design the best infrastructures to survive all of these extreme events that we know are going to be happening between now and 2100, and also be able to examine the financial risk associated with these increasing numbers of extremes. I wanted to step back a bit and talk about the energy water nexus. This slide was actually from a report produced by DOE back in 2016, but it's a summary of how the energy and water components are interdependent. This particular slide almost gives a misleading impression of how all the different energy water components do interact, because it doesn't show anything except the annual average. And on an annual average, all of the extreme events, the extreme phenomena that might last during a short-term drought, it's kind of washed out once you average out to a 1-year period. But if you look at a short-term episode, like a week or a month, some of these lines might actually disappear. And in those kinds of cases, it puts pressure on the grid. One has to look at the grid like this and examine how are all of these different choke points across the grid becoming vulnerable to different levels of energy water nexus. Is hydropower going to be more vulnerable under drought conditions? And is the grid stability going to be more vulnerable under different kinds of conditions? So getting a better handle on all of this is going to be critically important for the climate community. Again, I'm going to reinforce the point that extreme events in the climate models needs to be much more robustly treated, but it's got to be treated in let's say simultaneously with respect to how is the grid and how are all the energy components attached to the grid organized in a way with their own thresholds. In other words, are these thresholds going to be exceeded in different ways during different types of extreme events? And these are not just local events, but these are events which can span geographically across an entire Western region because of the interconnectedness of all of these various grid components. So I've mentioned the word integrative a number of times, observations, modeling, simulations, but I wanted to get into a little bit on the research side just to make a few points for illustration. So as a scientist, we often try to define framing questions which we can use to at least set out a research agenda on what's the most important path forward for our community. And for the first one, I wanted to mention that we have combinations of thresholds for components within any type of system. So if we think about the energy system, all the different infrastructure components have their own individual thresholds. We have system level thresholds. And whenever you have an exceedance of some kind, you take the risk of a blackout occurring. You might take a risk of a cascading failure occurring. But it's really important to understand from a meteorological perspective, how often could these risks occur and what types of extreme phenomena can we expect within, let's say, locally, regionally, or even national, globally, which can lead to these conditions. And that gets to the second point, is that what's the mix of meteorological precursors distributed over a region, and how can these mixes lead to things like cascading failure? And that's another big issue. And the final of these three questions is what can be inserted into, for example, the electric grid, other types of operations, to at least minimize those risks and offset those risks in some way to at least maintain that big national challenge what the public actually demands, and that's affordable and uninterrupted services. So if we look at how we do research within meteorology, we often look at model development and model into the operations world based upon grids. And these grids are often constrained by computer power. This is just an idealistic slide I took from a presentation I gave actually a decade ago, but it's just the idealized presentation of how a weather model is set up, or even a climate model. And the point is they break the atmosphere into different types of volumes as grids. And the challenge is, how do we get those grids to higher and higher resolution, at least from the weather side? But from the climate side, these grids have to get to higher and higher resolution also for the ocean and also for the land areas. So that's a challenge. It moves us into what we call non-deterministic and stochastic modeling, but it's getting into hydrostatic and non-hydrostatic predictions. And for non-hydrostatic, we're starting to build in let's say, the turbulence closure terms of these equations, which actually demand almost exascale computing. This is something which DOE has been working on for several years now. But the demands are increasing in a way that if we're going to go to higher resolutions approaching 3 kilometer or even 1 kilometer in the future, it's going to put a lot of pressure on the kind of computing which we're going to require. I'm going to put a plug in for DOE, and I'm approaching my last slides now. We've been developing within DOE something called the Energy Exascale Earth System Model, or E3SM. I gave a preview of this in Copenhagen a couple of years ago at our last big meeting. And at that point, we were just conceiving of the idea of moving from 25 kilometer to 3 kilometer resolution. And I would say that we're actually almost at that stage now. Later this year, we're going to be converting our E3SM model to a 3 kilometer model by incorporating what's called the SCREAM project, that particular submodel on the lower left. And SCREAM stands, actually, I've got to remind myself what SCREAM actually stands for, but it's the Simple Cloud Resolving E3SM model. And that, or atmospheric model, and that particular model is a non-hydrostatic system designed at 3 kilometer global for the entire planet. And it's able to resolve really high resolution phenomena, almost in a way that demands an exascale computer. Now, that's not alone what we're trying to develop within DOE, but how do we blend that with observational systems to at least further advance these models, build an uncertainty quantification methodology on top of it? And we're using one of our user facilities that's called the ARM facility to at least build those test beds for UQ, for uncertainty quantification. And the lower right-hand figure is just an illustration of how these observational test beds combine with large eddy simulation to at least provide the stochastic representation of turbulence down to a 25 meter resolution. So at least this is our vision within DOE. And granted, it may have sounded idealistic 2 years ago in Copenhagen, but we're closer to reality with this. And I think we're at the stage where we need to talk more robustly with the entire energy sector, people on this call, to figure out how do we make this more of a reality where we can segue and transition the scientific capabilities more rapidly into, let's say, operations and the utility that we see here. So the ideal approach, and this is one of my last slides, and that is we do need to develop demonstration projects which tie science into energy engineering, into some real world studies, but also look at these anomalous meteorological and wind shear events so we get a better handle on not just what the scientific opportunities are, but how do we actually segue that into, let's say, more real world demonstrations. In that regard, there's something called co-design we've talked about within DOE for a number of years, and that is you can co-design a scientific agenda with an engineering agenda. And that might be an opportunity to consider. The third one is something we started in September of this past year. We called it the AI for ESP. Many of you might have heard of this. It's called the Artificial Intelligence for Earth System Predictability. We're going to be holding a workshop probably this fall to figure out how do we incorporate machine learning with prediction models that extend not just into the models themselves, but the observing systems that are used to provide data for assimilation into those models. But ideally, we need to figure out what are the uncertainty quantification methodologies that can be beneficiaries of machine learning and demonstrate that to energy designs and financial risk. This is a long-term agenda, which will take multiple years, but at least it's my agenda within DOE to at least not just wait for scientific discovery to kind of migrate into operations, but how do we develop a more robust handshake to accelerate that process? I think that was my last slide, so I'm going to say thank you, everybody. I think at this stage, I'm going to pass it back to Mark, and we'll go on to the next phase of this hour.
Oh, thank you, Gary. This is very, very good. I think you have a very unique perspective in terms of really kind of setting the research agenda as funded by DOE. What's, where are the researchers actually putting their efforts and their funding. One thing that's not clear to maybe some of us that are closely on the energy side of this is just how much of a driver is the energy system customer base and stakeholders versus other things. Because I know the weather enterprise has so many different stakeholders. How do you feel the pressures of who is really helping to set the agenda and maybe in your view, helping to nudge it in the right way at this point most effectively?
I think the real people are the ones, I hate to say real people, I think the people who have the biggest impact are the ones who are kind of in the middle. They're working with the energy community and the meteorological community. So there are some national labs within DOE which are actually right in the middle of that. I mean, NREL is a classic example of that. But I would say all the labs are dancing on both sides of the fence. They're dancing on the science side and on the energy side. So it's identifying those people who actually are trusted within both communities. And I think that's the best path forward, is to get those people more visible in workshops like this. And I think we're going to see more of that with subsequent events with this workshop over the course of this month.
So you do see the energy sector and the topics we're talking about at ESIG as being at least one of the major drivers of the research agenda?
I do.
Yeah.
I do.
The other thing where you've had a lot of experiences in the marine meteorology. So we have to discuss offshore wind a bit, which has been a very strong European activity and now starting to happen on the east coast of the U.S. I mean, and also that's been a major interest of Department of Energy in getting ready for that launch as well. Do you see that continuing, where a lot of the attention will be on the offshore meteorology?
I've been hearing that. It's not necessarily new. You're probably aware that I worked in Denmark for quite a few years, and that was my introduction to the wind energy community, was when I was working in Denmark. They have a different type of approach within Europe. They are almost forced to pay a lot of attention to offshore production, but they are also in a region which is a little bit different than what we face here in the U.S. And that is that it's relatively flat terrain when you get over to a place like Denmark. But if you're going to the west coast of the U.S., it's a totally different type of meteorological regime. And it's the same thing with the offshore of the east coast U.S. It's a different kind of meteorological regime. It is an opportunity, because when you're offshore, you don't face the same type of constraints. But again, from a scientific perspective, these create opportunities. Scientists are always looking for problems to solve. And I would say boundary meteorology, which is a favorite of mine, that is a sweet spot for at least looking at some really hard, exciting problems that the wind energy community is throwing at us. So I would say thank you to you guys for doing that. But at the same time, we need to work together to figure that out.
Yeah, it's been very interesting. And Department of Energy, of course, has funded some excellent work on like the wind forecasting improvement project and then the solar forecasting improvement project. So we've talked about those many times over at ESIG meetings in the past. And part of it also was you talked about the exascale computing and going to higher resolutions or sometimes hyper local type forecasts. I mean, is your view that there's actually a lot to be gained by going to higher resolutions and getting better forecasting, as opposed to better formulations of the physics and things like that, more of the core research on that? How much traction do you think there is yet in just getting faster and faster computers and higher resolution models?
So I would say there's a lot of good traction within DOE. And I think that's illustrated because at least within the community which I support within DOE, this is the climate community, which is really taking advantage of exascale computing. We wouldn't be where we are. We wouldn't be where we are today without having jumped on that exascale train. Mm-hmm. So I would say there's a lot of good traction. The other is that a lot of the uncertainties and a lot of the extreme events which people worry most about demand high resolution modeling. And it's not just a high resolution anomalous event, but if you have a, let's say, an internal boundary layer during stratified flow for offshore conditions on the East Coast, it'll appear to be somewhat stationary, but there's enormous spatial variability in the kind of meteorology you can encounter.
Right.
And that can only be handled with a high resolution model. So I think we're stuck with exascale to make progress, and I'm excited with it. A lot of the other agencies are paying very close attention, but they're letting DOE kind of work through the kinks in exascale before they jump on board in full. I would say large agencies like NOAA, which are more on the operations side of meteorology, they don't have the kinds of capabilities and computing DOE has, but they're watching very closely, and they're working together with us to make sure that they can take advantage of the lessons learned, which we're going to be providing.
Yeah, it's an interesting challenge for those of us in the industry because we need those operational forecasts and we need the climatology as good as we can get it to look at this long-term risk you mentioned. But it's often a challenge of how much time and expense can you put into like analyzing a given project, for example. Also on the climatology side, I mean, do you see higher resolution models being part of the answer there as well, or how are we going to deal? Because you raised this excellent point that from the finance side and to some extent from the resource adequacy market design point as well, which is another big topic of this workshop. We're looking at this multi-year decadal risk, right? And what's the uncertainty? Even before we talk about climate change, sometimes just how certain are you in the cash flow of this project, right? You see climatology models making similar progress, and what's the best pathway for them to advance?
Yeah, I would say it's the same. Climatology, that's not a new field, you could say. I would say a number of countries have been developing wind climatology atlases across the planet. In fact, when I was in Denmark, they had developed one of those years ago, and they continually upgrade those. They do that here in the US. I think NREL has some stake in that. But the point is, people have often thought about wind energy atlases or wind energy climatologies or solar power climatologies from the atmospheric surface layer. They hadn't thought about it at the hub heights of the big wind farms that are being under development now. Mm-hmm. That makes it a little bit harder. So I think we're going to have to put some investment into upgrading those capabilities for the full boundary layer, not just the lower surface layer up to, say, 150 feet. We need to get up towards 700 feet or 1,000 feet. And when you're up that high, that's where you start to see a lot of these anomalous meteorological behaviors, like low-level jets or internal boundary layers, which could complicate things.
Yeah, we did a lot of work on that on the first wind forecasting improvement project around the Midwest with the wind speed pattern and direction is completely different up at hub height than it is down at 10 meters, right? So It's going to be very interesting work. Well, the other hot area, of course, is solar, and that really gets into a lot of the cloud dynamics and things like that. Are you seeing similar advancements? And I know that the solar forecast improvement projects, I think, have been very useful, are coming up with better modeling and capabilities as well.
Yeah. I think at least on the climate side, we're starting to make progress now with higher resolution models. DOE, as you might know, actually, the framing issue behind my division is cloud aerosol interactions. And I would say that's going to be a major component as we go forward in time of doing improved solar forecasting into the future. And when I mean solar forecasting in the future, I'm talking about climate time scales. How could let's say the solar potential change over time as the climate warms? That's going to be it's an important topic.
Yeah, and to bring this toward some of the power sector issues here, obviously, kind of the gorilla in the room these days has been some of the extreme events like we saw in February around a large part of the country and certainly impacting the the southern Midwest and Texas region quite dramatically. And we're going to have a lot more discussion of this, including on Friday's opening plenary, where we'll go into a lot of detail of meteorology around this and so forth. But, you know, there's still some debate, I think, about, you know, what's really driving some of this. Is it truly climate change that is causing the more extreme events? Or to some extent, is it the systems themselves that are also being transformed and making our power sector more weather sensitive? You know, and then how much of that is really weather within the norms of, you know, of what you'd expect over long-term weather variation versus climate change, and how we start bringing that in.
Yeah.
You know, do you have any advice for us? And we'll be going into more detail, I know, but just general advice in terms of how we actually do this merging of understanding climate change versus extreme weather.
Yeah, well, there's no doubt we're going to be seeing changes in extreme weather as the climate warms. We're making sweeping statements on that right now. And if you look on the macro scale, it's sweeping statements. But we all know that intuitively, there have to be changes in extreme weather. What we don't exactly know is the degrees of variability of that extreme weather. Because, you know, there's a lot of internal variability anyway within the climate system. But what people are putting a close eye on are how our, let's say, things like the El Nino pattern, is that going to change? Because if that changes, it creates a domino effect on how mesoscale systems might change. Mm-hmm. But it's open to the science. We need to figure that out.
The other thing that's come up a lot in some of these recent events has been kind of the correlation between multiple, not just multiple weather variables, you know, that impact energy for, you know, different mm-hmm. parts of the energy sector, but of course correlations within the energy sector itself. Like, you know, we didn't realize that you know, you actually could not cut power to gas you know, generation, because that's going into the power sector. A lot of cross correlation. So when it comes, top question we have rated here is, you know, how can power system planners really account for whether this weather variability and the changing trends we're seeing from climatology and extreme weather? Do you have any advice on how we might want to start rethinking how we do system planning on the energy side?
That's a tough question.
Yeah.
I would say we just need to work with our labs that are paying close attention to the latest scientific results as they come out. Because as these models get to higher resolution, we're starting to get different perspectives on how the climate is really going to unfold. I think we just need to have much more interaction between the scientists and the energy sector, because developments are happening quite rapidly, and if we can't wait for the assessments every 2 to 4 years, because they're often obsolete by the time they happen. Right.
And I know looking at one of the, Stephen here from Australia was asking, I mean, ESIG does have a lot of international members and a lot of participants actually from Australia. We're learning a lot, sharing a lot there. And he points out too that Australia on the meteorology side, their Bureau of Meteorology has been looking at multi-factor analysis of the correlations of low wind speed and high temperatures that might, you know, affect multiple generators in the system and so forth. Is there a lot of similar analysis going on in some of the research programs or labs, government labs that you're familiar with, really looking at how these multi-factor issues might align with issues in the energy sector?
There are. I would say it's confined to just a small number of our labs. I would start with NREL, because they're in the middle of all of this anyway. Mm-hmm. Otherwise, I couldn't really help you too much on that one.
Yeah, definitely. And I know another hot area has been on the sensor and the assimilation side. You know, a lot of work's been going on with SOIDAR and LiDAR devices and other profilers and so forth. How much of your research and budget is really going into the sensor and the data assimilation side of this to get better ground truthing into the process as well?
Yeah. Well, there are a lot of, okay, there's a lot going on in the LiDAR community. In fact, one of our labs is trying to develop a quantum LiDAR.
Really?
Ultra high resolution. So I think it might be an advantage just to get some briefings to your community of what's in the pipeline within some of these communities. Because it's not necessarily exciting to hear about what happened last year or a few years ago, because we already know that. But I think what the possibilities might be with some of the technologies under development that might have capabilities in 1 or 2 years. But we can talk offline about that.
No, I think we'd be very interested in that in future meetings and get more input on this. Going back to the extreme events just a moment, and kind of it was picked up by one of the commenters here, and a question of my own. Yeah, I think we're starting to see some things like what happened in the Texas region, where it may not have been climate change, but it certainly appears to be a very extreme event, and you have so few occurrences of this. You talked about bringing into machine learning methods and so forth. How well will those work when we're dealing with those edge events where we don't have a lot of historical examples to use for training? And does that really have to lean on the physics-based modeling and just really get that right? Or can we start to actually apply machine learning methods to these edge cases?
Yeah, that's a great question. Just for, I wouldn't say for the fun of it, because it's really an exciting area we're trying to develop. We solicited some white papers from our national laboratories a few months ago to come up with ideas on even the wildest ideas. We asked, what are the wildest ideas, and how you can incorporate machine learning to advance the predictability of extreme phenomena. And I think that's going to be part of our workshops starting in, let's say, this fall. So I think we just need to keep a dialogue there, because there are some crazy ideas out there that might get some really good traction. And you're right. Sometimes when you're operating at the edge, you worry about not having sufficient training data to at least make progress. But people are coming up with ideas on using synthetic data as a start, and using large eddy simulation to create some synthetic data. I think there are some ideas out there. We're trying to figure out what's the potential here.
Excellent. Thank you, Gary. And the final question, for the attendees that are really power system engineers who don't have a lot of hands-on with meteorology or climatology type discussions before, can you recommend any reading or background? Where's a good place for such people to start? Do you have any recommendations on people trying to get up to speed on this?
Not off the top of my head, but I will get that to you. Let's put it that way.
That'd be great. We'll try to provide that along with any other questions you'd like to answer, Gary. I really want to thank you very, very much for a great presentation and great discussion here. So we are recording this, and we'll get the slides and all that out to you probably tomorrow morning when that's available, as well as any other input that Gary would like to distribute. I hope you can join us for the other sessions in this online workshop. The opening plenary session on meteorology and climatology is this Friday, and we'll be discussing in more detail the major weather-driven event in Texas and the Midwest in February. Then we will continue on Tuesdays and Thursdays during June for the entire month. Each session is provided at no charge, and you can register in the events area at ESIG.energy website, and you'll get a separate WebEx link for each of the panels. Remember that our online workshops and monthly webinars are free and open to everyone, so please learn more and register at esig.energy. And if you aren't getting our monthly newsletters, send an email to info@esig.energy to be added. We do archive all of our webinars and meetings, and you can find all that at the website in the events area. And please also check out the blogs from leading energy and meteorology experts when you're there. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks for your participation. We hope to see you in person soon. Thank you, Gary. Much appreciated.
Thank you, Mark, and thanks, everybody.